80% of my day, okay? I sit in the dark. I sit in a dark room all day. It's hard to stay awake sometimes because it's dark, I mean, to be honest. But I've been doing it for 11 years, 11 and a half years, so I guess I'm sort of used to it by now. But anyway, fluorescent microscopy, again, this is sort of the gist of what we've been driving towards. It's probably the main thing we're going to end up talking about, and which we'll be using the most. And all the other talks you've seen so far by the other speakers have all obviously involved fluorescence microscopy of one form or another. It's the, I guess it's the pinnacle of optical microscopy, okay? Okay, so yesterday we looked at H&E slides and stuff, and we talked about, you know, if you do a paraffin slide embedding, you get better morphology, okay? And we talked about some white light techniques. We talked about phase contrast, differential interference contrast, Hoffman modulation, just ways to look at unstained things. So when you look at transmitted light, you see morphology. And like on the first day, when he talked about, I remember he talked about the people in the stadium, and you'd see like one person had like a green dot or something that was fluorescent, right? Well, here, if you just look at fluorescence, and we assign them different colors, there's an awful lot more to see, okay? It can bring out a lot more detail. We can use tags. We can basically isolate a molecule to look at using fluorescent techniques. So I guess the take-home message to start with is, he talked about this a little bit on the first day. What is fluorescence? Again, not a physicist, not a chemist, a biologist. But basically what it is you have an absorption and a re-emission of light by an outer shell electron. So light is pushed into the system onto the what we call fluorophore, is the molecule that will fluoresce. We call those fluorophores. Okay, and what will happen is the electron will get kicked up to an outer shell, and then when it falls back down, it emits fluorescence. Okay, so what they say is fluorescence is redshifted from the excitation light. This is called the Stoke Shift. So we'll get into this a little bit more, but Stoke Shift just means basically the difference between your excitation and your emission. So everything we're going to be talking about today is you're going to have one light exciting, and then the fluorescence will come out at a different one, at an emission wavelength. Okay, and of course we show these as spectrums, right? Because we're scientists, we like to have graphs, we like to have spectrums and such. So this is one of my favorite dyes, and it's actually called, if you look down here on the bottom, Alexa 488. It's a green dye. The reason I know it's green because I work with it all the time. But the other reason is basically it has the color of the emissive wavelength, which is the red. And it's in the 500 some range, the peak. So that's your green spectrum. So if we put Roy G. Biv up here, V would be down here and R would be up here. So it'd be like Roy G. Biv, okay? So this is the green area. That's why this is a green fluorescent molecule, okay? Does this all make sense so far? The Stoke shift would actually be between these two, the difference between the emission and the excitation, okay? This one's called Alexa 48. Again, one of my favorites. The Alexa dyes came out 10, 12, 15 years ago. They're very, very well-made dyes. They work very well on a confocal. They're very bright, and they do not bleach. And what I mean by bleach is, when we go back a couple slides, this ability to be pushed out to the outer shell and come back and fluoresce. This happens again and again and again and again. Alexa, it can happen again and again and again and again and again, and it won't fade. But the older dyes that some of us here probably have used or you've seen in your labs might be called FITC, fluorescein isothiocyanate, FITC. Again, a green dye. But that's, like when I did my PhD, that's what we used. But with the advent of lasers and brighter lights and stuff, FITC just, it tends to bleach, okay? So if you can avoid using it, you're better off, okay? Especially with the confocal here, because the confocal will just crush FITC. It will not hold up and last. The dye will bleach and it just won't work anymore. I mean, sometimes you're forced to use it just because you have an antibody that's tagged with it or something like that, but if you can avoid the FITC, try to. The Alexa dyes are fabulous. I mean, I'm not getting paid by the company, but I just really like them because they work well. Okay, so how does this work? how does a fluorophore work? Well, basically what we were saying was a photon gets absorbed by the fluorophore. It's all or nothing. It comes in at a specific energy or wavelength, okay, and then it gets emitted at a specific and lower energy. So, for example, Fitzy, the green, would absorb at 488, which is a blue color, and emit at a lower wavelength, a green color. So when we go on the confocal, you'll see, okay, let's look at red fluorescence. And the weird thing is, you'll look at the light coming through the objective, it'll be green, okay? Even though it's red fluorescence, because what it is, that's the excitation light. It's green excitation light. It's a higher energy light, okay? So even though it's green coming in, the emission coming out will be red, okay? So there's this shift, this Stoke shift going on, okay? It's a little confusing, but once you start doing it, you go, oh, okay, I get it. Okay, so yesterday we talked about make sure when you do an experiment with the microscope that the microscope can see your dye, okay? Because there are now literally hundreds, probably thousands of different dyes and fluorochromes and such. The companies just keep making them left and right, constantly. This is like just part of a page of a catalog, and you can tell it's an alphabetical catalog, and we just, you know, barely go into the A's, and you have this many right here. This catalog goes on for pages, okay? So again, I cannot emphasize again and again and again, before you even start an experiment, before you do anything, if you want to use the confocal here, go down and talk to them at the confocal and go, I'd like to do this experiment. What dye should I use? And he'll tell you the correct dyes to use. And then when you go do your experiment, hopefully it'll work. But if you use the wrong dyes, it's not going to work, period. They won't be able to look at it, okay? So, you know, like going back to this whole idea, keep harping on again and again because I see so many mistakes. Think ahead, think ahead, think ahead. Don't be afraid to ask questions. Think ahead. You know, don't make the mistakes, because the experiments are hard enough to make work anyway. So you've got to do them to the best of your ability, the most correctly you can do them to ensure success. So using the wrong dye is just, you know, bad, just bad. So how do we excite fluorophores? With light, right? We're going to go over to confocal, and we'll see the light coming through, or the microscope I use a lot at home, a wide field fluorescent microscope, I have a light that excites. Okay, so in the older days, we used to use these mercury arc lamps, and they look like little boxes, sort of like this. They have an adjustable mirror to line up the fluorescent light and stuff. You might see them on older microscopes. We have quite a few in our building. I actually still have one in my lab. These boxes get extremely hot. The bulb right here is very bright. It has mercury in it. It's a very bright light because we needed that power to you know, make the fluorophores, to make the electrons jump to get the fluorescence. You have these knobs to align it. It's sort of a pain. Sometimes I'll go to align one. I can do it in 5 minutes. Sometimes it takes me 25 minutes to align it correctly. It can be very tricky and very delicate. The other thing about these, in the old days, I had customers, these older ones, that would literally fry their computers. They would have this sitting right next to a computer. The computer would be on, and when you fire this up, it has so much energy, it throws out an electromagnetic pulse, and it would literally fry the computer, okay? So the old rule, and I think still the rule today you should follow, is anytime you turn on a fluorescent light, that's the first piece of equipment you turn on, and at the end of the day, it's the last piece of equipment you turn off. So first on, last off is a good rule to follow with fluorescence, because if you encounter one of these lights and it's by a computer, it will destroy it. I've seen it happen. I had numerous customers happen too. So mine, I put on the floor, like 5 feet away from the computer, so it can't do it, okay? But, you know, some people have to learn the hard way, unfortunately. Okay, again, very hard to line up. The other thing about it, the bulbs on this typically go 300 hours. These have counters on them to record how many hours it runs. There's a reason they have these specifications. Like if they tell you a bulb is supposed to last 300 hours, you know why? Because it lasts 300 hours. Because if this blows up and it goes extra time, then you have a mercury spill, okay? I mean, when I was younger, we used to play with mercury, but now we've learned that mercury is a big poison, so we don't do that anymore. And at Case Western Reserve, where I work, if one of these blew up, we'd have to shut the lab down. We'd have to bring in a hazmat crew to clean it up. So there's a reason they tell you these rules about how long they're supposed to last. So I think anytime you use a fluorescent instrument or something, there's something about the bulb life, pay attention to it for safety's sake, because it's not worth, causing a big accident over. So do not go past that time. It's not worth it. Okay. Okay. So, like I said, those kind of lights were around for a long time, and they still are a little bit. But they started coming out with these other ones that shine the fluorescent light. It's like in a box. There's a bulb in there, and it goes through something called a liquid light guide. And then it comes out this lens called a culminator lens that runs in the back of a microscope. And I'm sure this is probably the setup on this confocal here. Now remember, this is just the confocal, or the wide field fluorescent light. This is not the lasers we're talking about. This is what's called wide field fluorescent microscopy right now. So when I was in sales, this was awesome, because these came out. You don't have to line them. Okay? They last 2,000 hours. The bulbs cost a little more, but still. It's pre-aligned. And you don't get that bright spot in the middle that you have to align with the other one to get rid of. So they were really common. I sold these I don't know. This paid my kids way through college probably selling these things, because I just sold them because it was so easy, because it was like you don't have to align them. They last longer. They're brighter. I mean, they're just better. So they sold really easy. Okay, and then another way, of course, you can excite fluorophores is lasers. But we're not going to talk about that now. We'll talk about that more when we get to the confocal. Okay. So again, light is the heart of exciting the fluorescent molecules. Whoops. Okay. So what's the mechanism that lets you look at the difference here between the excitation light and the emission light? So what's in these microscopes is these little fluorescent cubes. They're about, I don't know, probably about that big. One of these will run you in the US, one of these, given the filters, would be about $1,300, okay, to look at one color. They'll last quite a few years. Mine last probably 2 or 3 years, the filters on them, because I use an awful lot. But what it is and we'll take a look here, but this is the heart of a fluorescent microscope, what's called the fluorescent cube, okay? And so what you do is you need to match. Like if you're going to use Alexa 488, then you have to use an Alexa 488 filter cube to work right. If you're going to use a dye called Texas Red, then you have to use a Texas Red cube, okay? So that's why I said you are limited by what the cubes are in the microscope to what you can look at. That's why check first, make sure, hey, the person has the right dye, or the person has the right cube to look at my sample. Because if not, there's nothing you can do about it, for the most part, okay? You're dead in the water, okay? Okay, so let's look at a basic microscope design and how the fluorescence is fitted in there. So right here, this is the fluorescence filter cube turret. And a lot of microscopes, you'll have like a little wheel, and you can turn it, like you go to the red filter, or the green filter, or the blue filter, DAPI, or Alexa 488, or Texas Red, okay? And I have one like this in my lab on my, what kind of microscope is this with the objectives on the top? Remember? We talked about this the other day. This would be a what type of microscope? Would it be an inverted microscope? Would it be an upright microscope? Ah, okay. It's an upright microscope, right. Okay. So I have one like this, and it's manual, and I turn it, and I have to take the picture. So the fluorescent light comes in. It goes through the excitation filter, which weaves out which narrows out the light in terms of wavelength. It comes down, it hits the sample, it bounces back up through that same fluorescent cube, and either to your eyes or to the camera, coming through the emission filter, okay? But that's basically the setup of it, how it works. Okay, so getting into details, the light comes in here. This has a certain cutoff. It only allows certain wavelengths of light through, okay? So this is where the specifications come in. You look in the catalog, and you pick the appropriate one that would say work with Alexa 488. It would only let light in. Remember we looked at that spectrum a few slides back? It would only let those wavelengths of light in, okay? And then the light passes through here, goes through a dichroic mirror, and then out, then up to the sample, and then it'll bounce back through the same cube, through the emission, and it'll bounce off the mirror and go back out. It sounds a little confusing, but basically the idea is you're narrowing the wavelength of light coming in, and you're narrowing the wavelength of light coming out, okay? Same idea here, just another way to show it. So light goes through the excitation filter, hits the dichroic mirror, comes in the excitation filter, hits the dichroic mirror, goes out the objective, it'll come back through, it'll pass through the dichroic mirror again, and it'll go, this would be out to your eyes or whatever. Okay, so emission filter, excitation filter. Everything's excitation, emission in fluorescence. Okay. Okay, so sometimes you might want to do a lot of these different excitations and emissions a little bit faster. Because like I said, that one I have, you have to, physically turn the turret to pick the different cube. My microscope's automated. My cubes like switch into place automatically. But then if you want to go a little bit faster, they have these things called filter wheels. So what it'll do is in the light path, this thing will spin like you program it, like a computer program, and it picks this one, and then it would pick the appropriate excitation on the other side. So in the middle of the microscope, you just have the dichroic mirrors. So you can go a little bit faster. So this one you could image like on the second scale. Like I used to do a lot of a dye called Fluorocore for calcium. And we go like back, forth, back, forth, back, forth. And we could look at maybe half a second, we could switch colors and take a picture every half a second or so. Which the very first talk here, Dr. Nair, his stuff was super, super, super fast that he was looking at. So as opposed to using a filter wheel, which is obviously faster than manual, faster than my cube changer on my microscope, they use something called a micrometer, which uses like little piezo galvanometers and stuff, and it can like switch colors that fast. Because if you want to see sometimes some like rapid calcium, signaling or something, you've got to be able to just go, 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 fast, fast, fast. Now, the other thing to think about it is if you're switching that fast, only a little bit of light's coming through. Remember what we talked about earlier? We talked about different cameras. So if you end up buying something like this, you want to go fast, you better get a camera that can match up with that. Okay? So this is not like, I buy a microscope, I buy this fluorescence, I buy this camera, I'm good to go. You've really got to depend on your sales rep to steer you in the right direction. And like I said, feel free to check with me, my knowledge just to put it in there, because if you buy the wrong stuff, it just won't work for your application. So you got to make sure you get the right stuff. Okay, what are the three main ways we use fluorescence microscopy in biology? Okay, and we're going to talk about these a little bit more as we go on. Okay, now the main ones basically are as an antibody, and we'll be talking about antibody staining. Has anybody in here done antibody staining? I'm sure probably some of you have. Yes, okay. And if you do Western blots, you're in a way doing antibody staining because you're putting an antibody on your blot, and then it's recognizing your protein there. And instead of having a fluorescent thing on a Western blot, you have what, a horseradish peroxidase often kind of tag. Okay. So antibody staining is one way. GFP, green fluorescent protein, which we talked about the first day. Dr. Nair's talked about green fluorescent proteins. I will get into more detail about this when we talk about live cell imaging. The fluorescent proteins are the heart of live cell imaging. So we'll talk about that. And if you've never seen a green fluorescent mouse, they're pretty cool. Let me tell you. You take the black light, you shine it over them, and they're green. It's like, wow, it's something to see. Because we have them at our institution. It's pretty neat. Sort of like a firefly, except the whole thing's lit up green. It's pretty weird. Or as a fluorescent dye. This particular example here was in my lab. What this was an angiogenesis assay where they would take cells and they would grow them in a gel, like a matrix gel. And they were trying to figure out how these cells would form patterns, angiogenesis. Angiogenesis means, what's angio mean? Any ideas? What was that? Right, angio, like starting, beginning, like Genesis is starting, beginning, angios with blood, heart. So this is an assay to look at how blood vessels form. So what we would do then is we'd put this dye in called calcine, which is an extremely bright fluorescent dye. Again, they checked with me and said, hey, if we use calcine, can we look at it? I looked it up on my chart, and I said, okay, it's a green, it's got this excitation, it's got this. Sure, we can use that dye, no problem, I can see that, so let's go ahead and do the experiment. They checked with me first, which was good. Okay, it's always good to check. I mean, I don't know how many times I'm going to say this. You're probably going to get tired of me hearing it or me saying it, but it's important. Okay, it's critical to choose the correct fluorophores to get good results. Okay, so here's a lab I work with, and what they do is they look at cells, and they're looking at something called autophagy. Has anybody ever heard of autophagy? So what autophagy is like when a parasite invades a cell, the cell goes to engulf it, to eat it, you know. Or a lot of times autophagy is as a cell grows and gets older, like some of its organelles die, like the mitochondria become bad, or parts of the endoplasmic reticulum or the Golgi. So autophagy is the cell literally will eat itself, will envelop those particles and destroy them and recycle them, basically. Okay. So what they do in that lab is they look at autophagy, and then they use a different color here to look at the parasite, and then we're looking at a protein that showed where the parasite interacts with the cell. So this was 3-color imaging we did with green, blue, and red. Okay. And again, I don't know if the blue was blue, but it's pseudo-color. I think it might actually have been a far red dye, but we made it blue just, so we could see it better. Because remember, they're not colors. They're fake. You just are applying colors to make it look the way you want. Because it's just photons. Everything's photons. Everything's math. Okay. So how do you choose the correct fluorophore? Well, I think the first thing is you go to the person running the microscope and you make sure, hey, it can work with that fluorophore. So that's step one. What are you trying to accomplish? This is where I started getting better with the animation. I started getting better with PowerPoint here. Okay. So do you just want to see one thing? Or are you just going to look at one protein? Let's say you're just going to look at actin or something like that. Well, if you're just going to use one dye, then my recommendation for the most part would be Alexa 488. It's bright, it's stable, and I bet if you looked at every fluorescent microscope in India, I bet 99% of them would have the ability to see green. Have the ability to see Alexa 488 because it's like the most common one that's just out there. I mean, Fitzy's been around forever. Alexa 488 is a real popular dye. Green is usually your best color to work with. Not to mention your eyes, being from the Department of Ophthalmology, your eyes see green better than any other color also. So green, I like it. Now the drawback would be, whoever talked to me about autofluorescence earlier, again, like I said, you want to work more out in the red because autofluorescence tends to be the worst in green. Okay. But for one dye, simple experiment looking at one protein, I like this dye. And like I said, most microscopes, because if you had to go to your friend's institution or take it somewhere else too, chances are this one will work for them. Okay, again, Alexa dyes are very bright, they're stable, they do not bleach easily, and they can handle a laser beating on them. They will bleach, but you really got to go after it to make it bleach. I like them a lot. Okay, so again, how to choose the correct part 2 here. Again, we talked about this a little bit. Try to avoid fluorescein isothiocyanate if you can. It's a great flow cytometry dye. In microscopy, it's a little bit, it works, but you got to be delicate with it. You got to be gentle with it. Okay. This is what I used back in my PhD days because that's all there was. There really wasn't too many dyes out there. Now there's thousands. Again, try not to use flow cytometry dyes. I get a lot of times I get somebody comes over and goes, well, I just did this on flow cytometry. Can you look at it? And I go, I'll try, but I can't promise you anything. And sometimes it'll work, sometimes it won't. But it's a crapshoot. Remember what flow cytometry is? We talked about that a little bit yesterday. Like the cell's coming through a hose basically and hits it with the color and looks at it. Okay. Okay. Again, flow cytometry dyes are for a quick positive or negative, and they have very different excitation emission wavelengths. The microscopes usually cannot handle. Okay. I was getting carried away here with the animation. Most important. Again, I'm saying it again. I know you're getting tired of it, but it happens every day in my lab. People come over and I'm like, I can't look at it. I'm sorry. Just make sure you can see it. Okay. Now, a lot of you talked about co-localization as your project or coming up as your project. Okay, and we'll talk about that a little more as the course goes on, especially when we go to Confocal, because the Confocal is a great instrument for co-localization. But before you start that, for co-localization, you want to make sure you have 2 dyes that don't overlap. I showed you that spectrum earlier, right? Okay. So the whole idea is to pick a set of dyes where there's no bleed through of your dyes. And what I mean by that is, you know, if you use a type of green and it emits into the red, then when you look at red, you'll be seeing the green also. They'll overlap. They'll bleed into each other. Okay. So what I use a lot of times, we'll see if this will work. It's a link to a website I use a lot. Okay. But anyway, what it is if we get it to work, it's a thing. I thought we had it on earlier, didn't we? We can take this out now if you need it to come out. Are you just going to get on the net? Okay. But what it is, it's basically a website where I can punch in Alexa 488, a different Alexa, another dye, and I can see the spectrums. So I can determine, hey, are they going to overlap or aren't they? Like I said, I use it all the time because the people I work with who know what they're doing, they come over and they say, hey, I want to do this. I want to use this color, this color, this color. Will it work? And we'll look it up first and we'll determine, yeah, I've got the right filters. I don't think I'll get a bleed through, and I'll show you the problem with bleed through here in a minute. Perfect. Let's say we pick this dye, Texas Red. Now, it's not the worst choice in the world, but if you look at this, so what this is saying, when I use the green light, I'm exciting here, okay? And then my emission is this darker green, right? And then when I do the red, it excites here, okay? And then it emits here. But look at right here what's going on. So if I excite green, okay, I could get some bleed through here. They could bleed a little bit, okay? There could be some bleed through here. There's also another thing we have to weave in is the filters themselves. But just for simplicity's sake, what you want to do, like if you're trying to do co-localization, it'd be much better if you use this and then you move something farther out here that wasn't close, that was farther out. Because then you have less chance of this bleed through occurring, okay? So let me show you why that's a problem. Does that all make sense? You want to spectrally separate dyes if you want to use two to try to keep them from overlapping with each other. Because here's what happens. So I get a lab, or I get somebody will come up to me and go, oh wow, we got this really great co-localization. We did protein A and protein B, and wow, they co-localize all over the place, and it's the greatest thing in the world. And I go, okay, well let's take a look at the pictures. So then they give me something like this. So the thing to look at when you look at co-localization, okay, like we say in the world, nothing's perfect, right? And very few things in biology are 100%. You know, they're maybe 80%, 90%, but 100% is really rare, and perfection is really rare. So when you see something like this, here's my green picture, here's my red picture, and then like we saw right before we left, we saw how to put the two pictures together, right? We put a DAPI picture with the Texas Red picture. So if I overlap these two pictures and I get this, red and green make yellow, and it's perfect. I mean, this is absolutely perfect. Every single red and every single green are right on top of each other. It's perfect. Okay, that's wrong. It's just wrong. This has bleed through written all over it. And so what I'll do then is I'll say, okay, what dyes did you use? And then we'll pull out the spectral viewer, we'll look at the dyes, and there'll be this big overlap, and they use the wrong cubes and things like that. So if you ever do a co-localization experiment and it's like this 100%, it's wrong. This is not reality. This is bleeding one color into the other color. Okay? It's a common mistake. People think it's co-localization because everything turns yellow, but it's not. This is just bad picking of fluorescent molecules and bad picking of filters. Okay, of course red and green make yellow, but not everywhere. It's just false. This is bleed through. I was getting good with the animations. Okay. This is more realistic. They used a red dye on the left panel, a green dye in the middle panel, and then look, it only overlapped in certain places, okay? When you do co-localization, you're going to see something more like this when it actually works because, like I said, it's not 100%, it's not perfect. So keep in mind, those of you who want to do co-localization, if it's perfect, it's wrong, okay? And the biggest thing is if you see something fluorescing off, the piece of tissue like just a little bit of fluorescent stuff, and it fluoresces in every channel like that, then you might have a problem. Okay, so everything we've talked about up to this point has been about fluorescent wide field microscopy. Okay, wide field's the most common and easiest and cheapest type of fluorescent microscopy. I mean, it's expensive, don't get me wrong, but it's much cheaper than getting a confocal. This is the workhorse scope of starting a lab. I would start with one of these because you can do an awful lot of experiments with these things. You can do an awful lot of things with this kind of scope. I mean, this is my workhorse at work. I mean, I'm really good at running it. It's part of it. But, you know, my charge, so in my place to come run on my scope, the wide field, if you're in my group, the eye researchers, it's $9 an hour, okay? If you're not in my group, it's $15 an hour. If you go to the confocal microscope on campus, it's $45 an hour, okay? So usually what people do is they come see me to see if the experiment even worked, and then they need that real pretty confocal picture, but better to come see me with this scope. We can figure out did it work, didn't it work, and if you really need the confocal, then we'll go to the confocal. Okay, so again, but for a lab just starting, or for a good workhorse instrument in a department, this is a great thing to start with, I think. Okay, sometimes the confocal's just too much. Okay, it's overkill. And we'll talk about why that is when we get to it. Okay, it does a really nice job in X and Y. The Z resolution on it, fluorescence, a little weak compared to a confocal. It can go very fast. If you have to go fast, the wide field's perfect. The images from the first day where he was going really fast were wide field images. It's pretty simple to use, and it's, you know, relatively cheap. And the other thing is for live cell. Now, we haven't gotten into live cell yet, but we will. This type of light is not as toxic as lasers in general, okay? So this is a good way to do live cell imaging with a scope like this because it doesn't have the power of the lasers. And you have quite a bit of control over something like this. So it is a good live cell setup, okay? This is what I do all my live cell stuff on. I mean, once in a while we have to go to confocal for something special, but for the most part I'll do it on my wide field scope. Okay, and then you always hear, oh, well, because my thing is I always get people come and go, well, I want to go to confocal because I want a pretty picture. It's better. And a lot of times it is, don't get me wrong. The confocal can definitely give you a prettier, better image. But if you know what you're doing, you can get stuff like this off the wide field, which is a pretty fabulous image, actually, I think. Again, it all comes down to your preparation of your sample. If you do a really good prep, you bring me something like this, I'll get you a picture like this. You bring me something bad, right? What was it saying yesterday? Garbage in, garbage out, right? It's the prep. The prep is, you know, everything. Okay, so the one thing I have on my particular microscope is I have automated filter changer, so I can change my colors automatically with Metamorph software. And then I have what's called a motorized stage. So what a motorized stage is, it basically sits on the microscope, and it's the part you put the slide on. But mine can go around in X and Y and move to a certain spot. And it's a very precise instrument. So I can go to like this cell right here, and then I can program it to come actually back to that exact same cell, okay? Again and again and again. And on mine, I can pick multiple cells or multiple spots, and I can come back again and again and again. So by hooking up a motorized stage to a microscope, you then have the ability with software to create a time-lapse system, okay? So you can do time-lapse then, because you can visit the same point, program it to come back over time. So you can make movies like that with the motorized stage. And also you can do that tile scanning stitching we talked about earlier yesterday. Remember we talked about take the little pictures, put them all together. So here's an example from my lab. All these pictures that I use the motorized stage to take, because the motorized stage then gives the X, Y coordinates of each picture. The software then lines them all up, puts them all back together. It runs again, math. It runs a fit algorithm to make sure all the pictures fit. So this picture is real nice. This is retina, again. But this is 100 separate pictures put together. All because I have a motorized stage. And again, the motorized stage will let me do this, and a motorized stage will let me do time-lapse. And it's also nice too, because if I want to take 6, 7 pictures, I just pick the points, hit the button, let it take the 6, 7 pictures. So, I mean, I think if you're buying a system, I would think about getting, you know, put your money in your objectives, put your money in your camera, and if you have money left over, start thinking about a motorized stage next. I think it's the next most useful thing you can put on a system. Okay, we talked earlier, I think you talked about live dead assay, right? Now this wasn't live dead assay, but this was just dead assay, basically. So what it was is we were adding drugs to the sample to see how fast it killed the cells. So what this is, like what you're looking at here at the beginning, this is propydium iodide. Propydium iodide is like a red dye that will only go inside a cell that is dyed. If the cell's intact, the membrane's intact, the propydium iodide cannot go inside it. But if the cell becomes weakened, starts to die, the dye will penetrate. So this is a time lapse. And as we added the drug or whatever, you can see the cells just, this was in suspension. I think these were T cells, if I remember correctly. They would start to die as the nucleus took up the dye. Again, we did this as a time lapse. This is just one position, but we did multiple positions. We actually used some slides that had 8 wells, and we set up different conditioning in each of the 8 wells. And by using the motorized stage, we were able to do 8 experiments at once. We were able to travel between the wells and look at the different conditions. Okay, so again, the motorized stage is really nice for something like that. It lets you do a time lapse. And nothing like a movie to show what you're trying to show. It definitely helps. Okay, and yesterday we talked about phase. And what do we use phase for? For unstained cells, exactly. Okay, so I work with a lab. You know GNOM, right? GNOM was there when you were there? GNOM's lab? Yeah. So he does fungus, okay? So this was pretty cool, I thought. So I brought this one. I do a lot of this for them. I always try not to contaminate my area, too, because, oh my gosh, it's just fungus going everywhere. But anyway, let's take a look at this. So you can also use, you know, time lapse with something like phase. And the hyphae just explodes. So we do a lot of drug studies and stuff with that lab. That lab also does a lot of, their big thing is they look at catheters, you know, that get inserted in patients. Like they might have a problem, they'll leave a catheter into their vessel or wherever, and it might stay in there a long time. So they're trying to develop coatings that won't allow fungus to grow on the catheter. Okay, so we do a lot of experiments like this with them to look at the growth rate and if we can inhibit growth and, you know, different things like that. So that was 11 hours. So I mean, it grew really fast, but that was actually 11 hours. All right. We'll look at it again because it's pretty cool. Okay. Let's go on to the next one. Okay. Now, everything we've talked about so far, I said a motorized stage. That's just X and Y. Moving in X and Y, different X and Y plane. But if you add a Z motor, which is the heart of the confocal, being able to go up and down and do things we call Z stacks, like focus at different planes, then you can do Z stacks. Okay, so this will now be playing through this in Z. This is actually nuclei from just cells, stained with DAPI, the blue dye. So see how it like goes through them. It changes focal planes. Now, you usually would think of this as confocal, but I was able to do this on a wide field, okay? And I'll teach you a little bit about that when we start talking about deconvolution stuff. So you can use a wide field as a confocal to some extent if you know what you're doing. We call it poor man's confocal. Okay. The heart of the poor man's confocal, and we'll visit this a little more also, is something called deconvolution, okay? Add a Z motor to your wide field and some deconvolution software, you get a poor man's confocal. So it has its drawbacks. I usually only use it on cells because they're nice and thin. Something thick, it doesn't work so well. But look at the difference in the quality of these images. This is the exact same image prior to deconvolution and after deconvolution. See how the little details come out, get rid of a lot of this blur and stuff? Okay, so in general, what this is deconvolution, again, is math. It's a massive algorithm. And what it says is okay, we took these pictures, but nothing's perfect. No optical system is perfect. But what if it was perfect? If it was perfect, and we fed all this parameters in over here of what makes up this image. We fed all these different parameters in Z, all these different focal planes in, and we ran an algorithm that said, hey, what if this was perfect? We get this out. Okay, so a lot of times people don't even have to go spend the $40-some on the confocal, because I can come up with stuff that basically mimics it to some extent. Not always, but a lot of times I can get pretty good results like this that save them the trip over there and save them the money. So, like we say, poor man's confocal. Okay. Okay, I think that's the end of this section on fluorescence microscopy, which is like, again, the heart of this course, basically. So, questions? A lot of these things are real pH dependent too, especially the older dyes like Fitzy. So I've had people bring it over to me and the pH is off a little bit in the whole thing. I'll look at it, and as I'm looking at it, it just disappears. Like it can't continue to fluoresce anymore.
Is it only happening in lab cell imaging or?
No, I mean, there's ways to get around it, but if you can avoid it, you try your best to avoid it. I mean, if you have to work with it, you have to work with it. And we'll talk a little bit about how to work with it.
Already purchased it.
Okay, that's fine. But the trick then, what are you going to use it for?
The localization of some enzymes in the tissue sections.
Okay, are you going to use the confocal?
No.
Okay, so then you might be all right. The confocal is the worst at bleaching,
Okay.
so you might be okay.
Fluorescence is okay. Fluorescent microscopy.
Yeah, but the trick with that usually is what I tell people is you want to be gentle. You want to put the light maybe a little bit lower if you have control over the light. Make the light a little bit weaker, but make the camera, the exposure a little bit longer. So you don't hit it with as much light, but you use the camera more to pull the signal out. So that's sort of the trick, to use less light coming in, but use the camera at a greater ability to grab the light coming out, the photons coming out. So less photons in and grab more coming out, like use a longer exposure on the camera. But you might be all right. I mean, if you're just doing short time stuff, you'll probably be okay. It's just when you try to go for a long period of time, the Fitzy really misbehaves. Okay, but if you've already bought it, work with it, see what you do. If it's a problem, then you got to switch, but chances are you'll probably be okay. All right? Yes?
Why fluorescent microscope not giving depth images compared to confocal? In depth C-stack, as you told.
So what's the difference between the two?
Yes.
Okay. We'll talk about that now, because it is a good question, and it is sort of a good intro when we start talking about confocal. Okay. So we talked about wide field images, and the gentleman back here asked the question about what's the difference between that and confocal. Okay, here's basically the difference. Let's say that this line right here is what's in focus on my specimen. Okay, so we're looking at it in Z, and this is what's in focus, right? On a wide field microscope, light from above it and light from below it is all going to go to the camera. Okay, most of the light's going to come from here that's in focus. But if we go back a little, some of this right here is probably just a little bit out of focus, right? That's partially due to the light coming from above the focal plane and the light coming from below the focal plane. The wide field grabs all this light above and below. A confocal tends to just grab this, the focal plane. Okay. Did you ever do this? Like, you're looking, do you ever go like this? Like you make a little, with your hand, and you look through it? Like you make a little hole, and you look through it? You ever do that? Do it right now. Just take a look. What's it look like? The image looks, you see what? You see, it's a little cleaner, right? I mean, you don't see the whole room, but what you're looking at looks just a little bit sharper. Well, you're using your finger. You're making a little hole, a pinhole. Okay? On a confocal microscope, there's a pinhole. And literally, the pinhole allows this light from above to be not part of the image, and this light from below to not be part of the image. Okay? That's the whole gist of confocal microscopy. The light goes through a pinhole. A spinning disc confocal, it goes through a spinning disc with a lot of pinholes. But the one here you have is like a laser scanning. It goes through a pinhole. The pinhole gets rid of this light, gets rid of this light, keeps this light. The deconvolution software here uses all this information from above and uses all this information from below on a wide field image to determine what this should be. Okay, so that's pretty much the gist of the difference between confocal and wide field. Okay, but like I said, starting a lab, most of the things you can do, wide field's great. I mean, it works like a charm. But you know, when you need that thin plane, you need that real good focus plane, and we'll talk more about the other applications of confocal. Then yeah, confocal's the way to go. Okay, but expense. Okay, any other questions? What was that?
Alexa for double A dye, it's costly.
Costly? I wouldn't say that. I mean, I wouldn't say it's any more costly than any other dye. It's not outrageous or anything. But the good thing about it is it'll last, and it's a good solid dye.
Yeah, and in case we can reuse it.
Yes, I mean the dye will, like, usually what you'll do is you'll buy a tag to an antibody or something, and then that antibody, like anytime I get, oh, this is another good thing to bring up now. So let's say you did buy, we'll talk about secondary antibodies and stuff later on, but let's say you did buy a tube of this, tagged to a secondary antibody. So what I do when I get it, or initially, is I will aliquot it. I will take some out, put it in different tubes, and I will freeze it and set it aside. The worst thing in biology, pretty much any biology, is to put something in the freezer, take it out, put it back in the freezer, take it out. You don't want to take it out of the freezer more than once. Okay, freeze thaw is the worst. Where I'm from in Ohio, okay, we get snow, we get cold, right? You guys have pretty good roads here. Your roads aren't too bad. Our roads, because we have winter, so we get the water melts, it gets into cracks, it freezes, you know, ice expands, right? So we have freeze thaw all the time. Our roads just crumble a lot. And I think Shri can attest to that the roads are just, they get beat up, okay, from freeze thaw. Same thing in biology. If you're working with the sample, you're usually best off to take an aliquot into, like say you get 100 microliters. Make aliquots of 10 microliters. Freeze those other 9. Use that one until it's done. Then break out another one. Okay, that way you'll save your reagents and stuff. But yeah, that's the way to go about saving things. Is, you know, there's no sense having the whole tube sitting around if you're not going to use it. Freeze little bits aside, but don't go back and forth. When you start going back and forth, chances are it's just not going to work anymore, because that freeze thaw is really hard on biological material. Okay.
Like, slides, samples, you bought some slides as samples, right? For example, like, we have this Alexa 488 slides.
Okay.
We use this as a Fluorocore. And we show them the students for a class, and then again like that. So we are using the same slides for a long time.
Okay, right, because those, okay, I used to be a microscope rep. I used to have those same slides. They're expensive slides, but they've even got a little bit more speciality to them, so they will last again and again. I mean, I had my slides for 3 years, and I was a microscope rep. So they put some extra chemicals on it. I don't know what they do, but I know exactly what you're talking about. It's like your demonstration slide. Yeah, something a little extra there. And Alexa, again, is a very good dye. It will not bleach. But there's even some extra chemistry on those. Because I had the same thing. When I was a rep, I carried that in my pocket. Because, you know, you want to do a microscope. You want to use this absolutely gorgeous slide to try to sell the microscope. You know, you don't want to pull out some, horrible sample and go, oh, look at this. You want to pull out this super awesome. I think the slide I had like that was a $300 slide for one slide. So I don't know if you have the same one, but it's just a special, and it won't bleach for whatever the chemistry is. But I had mine for like 3 years. Yeah. Any other questions? Yes.
Can we avoid background noise in fluorescent microscope?
How can you avoid background noises with the microscope? Okay, so the best way to avoid the background noise usually is in the preparation. I mean, once the microscope takes the picture, you've already got the background. So when we get into antibodies and things like that, I'll talk to you a little bit more about how to block, especially antibodies where I see the worst background, how to block non-specific binding of fluorescently tagged antibodies, because that's usually the biggest background problem. The other thing is like somebody said today, the autofluorescence is a background feature too, of just the tissue naturally, you have no dye on it or anything, but it fluoresces. Okay, so again, on some situation like that, you might want to work with dyes that are more out in the red to try to avoid that autofluorescent background. Because the major backgrounds I see are autofluorescence and then non-specific secondary antibody staining, which we'll talk about. So it's all in the prep, and we'll talk a little bit more about that, but the prep, because once you take it to the scope, it's done. You know what I mean? There's only so many things you can do to try to correct for the background. So a lot of that's with the prep, and we'll talk more about that as the course goes on. Okay.
But when we do the live cell imaging, you know, we cannot actually stop all the backgrounds, right?
No, you're always going to have some. You're always going to have some. I mean, it's just inevitable you're going to have some, you're always going to have some background. The trick is, though, is to try to get the signal up as high as you can get it versus the background. And some of that's just a little bit of playing around with the exposure, trying to use it, because if you use a lot of the dynamic range of the camera, like if you can get your signal up to high numbers, then what you could do is we'll do a little bit here, and you know, this probably wouldn't be a bad time to talk about scaling and metamorph actually. So we got a few more minutes. I can go back to the image analysis stuff for a few minutes.
I think the GIAN come only at 350, huh?
Interactive session and quizzes.
Now? Okay, we'll do that.
And anybody can talk about the US education system in those aspects also.
Okay.
No, anyway, they are asking doubts, let them clear the doubts first. Okay.
Okay, we'll talk about that, and then I'll go back to what you're talking about. Okay.
I have another doubt. Like, you know, when we actually, the cell will have all the, like, you know, starch molecule, lipid molecules, things
Right.
like that.
You're always going to have some background. There's nothing you can do about it.
All these things will have the fluorescence.
Right,
And
right.
how do you actually distinguish that? I mean, that is not the thing we want.
Well, the thing is, though, your green fluorescent protein or your antibody should just be brighter than that to some extent. I mean, it might not be, how do you know it's really your signal versus how do you know it's not your signal? And a lot of that comes down to controls that you'll do. So when we do antibody staining, and like I said, I got a lecture on this coming up, but you'll put in a primary antibody, a secondary antibody. Okay, so you'll do one sample of just the secondary antibody to see where it sticks, or see where it's non-specific. And then you'll compare that to the one where you use the primary and the secondary. And by looking at those two, a lot of times you can determine that, hey, this is brighter, this is my real stuff, this is all my background. If you look at the two images side by side, you can sort of tease out what's brighter. But a lot of times when it really works, the signal is just, you know, 5, 6, 7 times more intense, and it just becomes really obvious that that's your signal. There's a lot of it. I think it'll make sense. But pay attention to this, because this is something that's sort of really important, okay? So when you grow up, right, and like I think we talked about the other day, when you grow up, you're taught what you see is what you get, right? Like what you see, you should believe. Okay. Okay. Now, if we just looked at these two images, okay, what would you tell me about those two pictures? What would you just say in general? Like, if I showed you those two pictures, what would you tell me? They look the same, okay? One of these is a good image. One of these is an absolutely horrible image. But they look the same, okay? Why is one good? Why is one bad? What did I talk about earlier? Remember what I talked about? This number right here, right? Okay. This is the same picture. I did this one at 27 milliseconds. I did this one at 5 milliseconds on my camera. If we go on this one where it's bright, look at the numbers. 2,000, 2,000, 3,900, 2,000, 3,000, right? If I come over here, 10,000, right? 12,000, 9,000, okay? They look the same, But the one on the left, or the 27 millisecond one, is a much better image because I am using more of my dynamic range of my camera. I am getting my numbers up higher. I am dragging the microphone all over the floor. Okay. I am using more of this. Remember what I said. If I can use more of this, then when I go down to do image analysis and such, everything is better. Life is easier. Life is better. These two pictures look exactly the same. They are not even close to the same. This is a very good image. This is horrible. Okay. Remember the pixels. Remember I said the most important thing is this. The data on this slide, on this image, is these pixels. Okay? That's the data. If I take this image and I make it look like this, you would say, that is horrible. That is just a lousy picture you took. It's all saturated, it looks horrible, right? It's the same picture. If we go to that exact same pixel, it's still 11,000 whatever. It does not matter what I make this look like. That particular pixel, if I could go back to that exact same pixel, will give me the exact same number because the data is the data is the data. The data is the intensity value of the pixel. It doesn't matter what it looks like. The data is the data. So if I said to you, shoot. Oh, here it is. I see it. I see it. I got it, Srijit. Now we've all drawn a bar graph, right? A bar graph. So if I had a bar graph, this is 10, this is 20. Can you see this, or am I blocked by the, can you see it? Okay, so if I had this bar graph, I want to roll off the stage, but if I had this bar graph 10, 20, 30, right? And I said, hey, how big would you make this axis here? Somebody shout out a number. 40? Is that what I heard, 40? 50, okay, 50. It's a nice graph. It's nothing special, but it's a good graph. So what if I made this line 1,000? I drew the line up to there. Right? If I drew the line up to there, what would you say about that graph? It would look stupid. Okay? It would just look silly. It would be absolutely silly. This stuff would look like this big, right? But guess what? It's the same graph. It's the same data. It's the same. Nothing has changed except how I look at the data. So in digital imaging, don't get fooled how the image looks. Okay? The only thing that matters is this, is the intensity value. Okay? It's all about that. That is the data. That's why I had that one slide where I said, this is the most important number on this whole thing. Because in the age of Photoshop and stuff, you can make it look like whatever you want. But the truth is, if I really wanted to compare these truthfully, this is called scaling. I'm playing with that axis. So to be truthful, if I set this at 16,000, my scaling, and 0, if I did the same thing to this one, this image over here, whoops, I have to change it to 5 millisecond. 14-bit scale. Make this 0. Pretty close. Pretty much the same. That's the truth. Now I've made the axes the same. That's the truth, that the one on the left is definitely brighter than the one on the right. Okay, that's the truth. In America, we call that apples to apples. Okay, but you guys don't really have apples here, do you? Not here. So I don't know what you call it, mangoes to mangoes or something. I don't know. But it's a fair. This is fair. I have my scaling the same. I have not, I have not done this and said, well, hey, wait a second. This image is actually brighter than this one. It's not. It's not the truth. I have manipulated how it looks. But when you get into the data of it, the data tells you, hey, it's not what it is. So digital imaging, don't always believe what you see. Okay? This is the take-home message of that. How we work, what we do there. Things have definitely changed. When I was working on my PhD, I'd say the labs ran from like 7 in the morning till probably 8 at night in general. I'm not saying everybody worked all those hours, but they were open then. Now the labs work a lot less in general. But a grad student in the US, I would say, probably puts in 9 hours a day, 5 days a week. And then chances are they'd put in, if they're in the lab, they'd probably go in Saturday 3, 4, 5 hours, and maybe Sunday a couple hours. So it's a continuous kind of thing in the US, the way they work. The way our system's set up is we go to high school until we're 18 years old. I think you're a little different here, right? But we go to high school, which is our local school in our town. We go there till we're 18, and then we go to college. And then we get a bachelor's degree. So usually that's a 4-year degree. So then from like 18 to 22 in general is a 4-year bachelor's degree. And then you go on to graduate school. It used to be you had to get a master's degree in between. Now you can go right from the bachelor's into the PhD program, so you don't need that. I have a master's degree, but it doesn't work that way anymore. So I think the main thing is that the hours there are a little bit longer for the grad students. And our PhD program, when you enter a PhD program, you have 2 years of classes also. So you will have 2 years of classes. And then after those 2 years, you'll work exclusively in the lab. But the 2 years of classes, you're working in the lab too. And the way we usually do it at Case Western Reserve and other institutions is you'll come there, you'll get accepted into a PhD program. So then they'll say, well, what are you interested in? You'll say, I'm interested in genetics or something. So they'll sit down with you and decide on maybe 3 labs that need people and have the money to support you. And then what you'll do is we call them rotations. You'll do, I think they're like 2 or 3 months. So you'll go work in this lab for 2 or 3 months. You'll go work in a different lab for 2 or 3 months. And you'll go work in a different lab for 2 or 3 months. And at the end of that 6 months or 9 months, then you decide which of those 3 you like, or maybe you don't like any of them. Okay, but it's good because, labs, a lot of hours, a lot of things, and there's a lot of personality conflicts. So it's not always just a science. So I think it's a pretty good thing in the U.S. the way we do it. Just with this, you get to check out a couple different labs or whatever. A lot of times somebody will do the first one and go, oh my gosh, I love it. I hate to do the other 2 rotations, but it's it's good just to learn different techniques and meet different people and do it anyway. Okay, but that's sort of the setup of how we do things. Again, I think I talked a little bit about this morning. It might be hard for you to get into a PhD program in the U.S. Thank you, Srijit. It does happen. Science in America is dominated by foreign students, without a doubt. Again, the Americans just don't want to do it. The time commitment's too long. The money on the back end of it is too small for most Americans. It's very I'd say it's a low percentage. The American students are probably maybe 20%, maybe. It's a lot of foreign students, depending on the institution. If you really want to shoot high and really aim high, the schools to go for are the Ivy League schools, Harvard, Yale, Brown, Columbia, which are mostly on the northeast coast of America, like in the states of New York, Massachusetts, Boston, up that way. Johns Hopkins is another great school in the Midwest. The institution I work at, Case Western's a very good school. Wash U, you may have heard of in St. Louis, is a fabulous school. I think Dr. Nair that was here had done a postdoc there. Wash U is a really good school. And now the West Coast has some very good schools out in California. Stanford's a fabulous school. Berkeley's a fabulous school. Okay, there's some very, very good institutions in America for studying, and it shows because we do get a lot of foreign students. An awful lot of foreign students come to America to do their postdocs and such. Is it hard to get in? Yes, I would think it is hard to get in. And like this morning, we talked a little bit about, if you get a chance to go to a meeting and actually meet somebody in person that you'd like to work in their lab, I think that really goes a long way. because it's not just an email then that they see. They actually see you, and they meet you, and they can talk to you, and they remember you. So again, it's a like most businesses or endeavors in life, it's a people thing. It's a people thing. So if you have the opportunity to meet somebody, that's great. But here, you know, if you have a friend here from India that started a lab in America or whatever, obviously that's a great opportunity, right? You work for an Indian woman in Cleveland. And you do see that in a lot of labs in America. You see a lot of, you know, a Chinese lab, a Chinese PI will have a lot of Chinese in their lab. Or Indian have a lot of Indians. And same thing, Germans will have a lot of Germans. Okay, I guess they just, you know, feel more familiar with people of their own country. So you do see a lot of that.
In science also, in science and social science, they do the same. You know, social science students also have to go and work with different group of people for like tryout like that. In social science.
I can't really comment on that because I really don't know, to tell you the truth. Just to be honest, I don't know how it works. I can only comment on really like biomedical science and stuff. I mean, even different departments in case like chemistry, I'm not even sure how they work. But at least the biomedical stuff I've seen usually works like that. And then our general rule for PhD in our country is, you know, you do your coursework for your 2 years, then you have a qualifying exam, we call it, which my qualifying exam was basically sitting in a room and writing for 8 hours a day for like 3 days over pretty much everything I had learned up to that point. It's a pretty intense exam. Most people get through it, I would say. But once you get past that, then you just work in a lab. And then the general requirement in America usually is one publication, first author publication, and another one submitted, and then you're able to graduate. Okay? That's sort of the general idea to be able to graduate. Some have a requirement of 2 actually published. But usually they'll like you 1 published first author, and then 1, at least it's submitted, then you're able to go. So that's, I'd say average PhD in America is probably in the neighborhood of 5, maybe just a little bit more than 5 years, probably, in biomedical sciences. Same here? Yeah, the 2-year course work's part of that, right? Because even though you're in coursework, you're still working in the lab a little bit, just not full-time yet. But it's usually a 5-year endeavor. Mine was 6. I happened to switch labs in the middle. I had the misfortune of just, I don't know, the first lab I picked. Now, there's a little bit of a story here. Is the first lab I picked, I worked for a gentleman. He was a real nice guy. I really liked him as an individual. As I learned more, I realized that he maybe wasn't always being truthful with me about things. Like, I think he gave me answers that weren't, you know, he always came up with an answer. He always told me, oh yeah, this is okay or this. And then I realized a lot of that stuff wasn't. He was just, I don't know, making it up or whatever. So, I mean, I liked the guy, and I felt really bad, and I remember going into his office to quit, and I was like, man, I feel really bad about this stuff. I feel really bad about quitting. Because I'm not a quitter, you know, but it just wasn't going anywhere for me. And I walked into his lab, and I talked to him, and he goes, and he listened to me, and he goes, you know what, he goes, sometimes in life, you just have to take care of number 1. You have to take care of yourself. He goes, I think you're at the point you have to take care of yourself. So he goes, don't feel bad. He goes, you're doing what you have to do. And I switched labs. I got in a really good lab. And the woman taught me an awful lot, and my career really took off. So, if you're in a lab and things aren't working, you know they're not working. Don't be shy. Sometimes you got to switch. Okay, especially in America, it happens all the time. We have people switching labs all the time, like personality conflicts or things don't work. But the most common one now, unfortunately, is the lab runs out of money, and people have to switch labs. So it happens a lot. But the research in general in America is pretty good. We have tons of equipment. I mean, you'd be amazed if you walked in a normal. I mean, there's so much equipment. There's usually not even space on the benches. There's just so much equipment. I mean, we have multitudes of equipment. We have money coming in like crazy. I mean, you always hear this, America doesn't have any funding. America has bad funding, and it is less than it was, but I mean, we have just tons of equipment. I mean, we have, like my department is 1, 2, 3, 4. We have 5 labs in my department. So we have we help other labs too, but we have a dedicated microscopy core, a dedicated histology core that does all the cutting for everybody, a dedicated tissue culture core that will grow cells for you, a dedicated genotyper to genotype all the mice so your lab doesn't have to waste time doing that, okay? And that's just for our department. I mean, we have tons of resources. Like my group to support eye research is like a $2.7 million grant for 5 years. So we have usually we have tons and tons of money. I mean, you hear this, we don't have as much money, and we don't, but we still have a lot of money. I mean, we can't sit here and fool ourselves. We have a lot of equipment. And like I was telling Madam yesterday, a lot of times we'll buy equipment and it just maybe gets used once or twice and just sits on the shelf and nobody ever uses it. It's really a waste sometimes. But American labs are very well stocked. And the super labs, like the really big hitter labs, they have just tons of money and just can do tons of things. Like I work with the lab, Chris Palczewski, probably one of the top retina researchers in the country. He has 17 postdocs in his lab. And I mean, they have just so many things going on and so many experiments running. And it's just, it's like an army, his lab. So there's some really big labs in America, really good, really top notch. And a lot of times, I wouldn't say all, but a lot of times you get in a really good lab like that, money's not even an object. He just says you buy what you need, you go do. So it's a different world to some extent. But this is at the bigger institutions. Don't get me wrong, smaller institutions struggle, they don't have the equipment. But the bigger research institutes are pretty well funded, I would say, in general. Yes?
Excluding the big labs, as you said, super labs, whatever, what's the general trend compared to European PhDs and postdocs and American PhDs and postdocs in terms of timeline, quality, publications wise?
Okay. I would say in general, and this is my opinion. Okay, I can't say I've ever looked at statistics in general. But I've always thought, my opinion working in this kind of stuff for like 20-some years is, I always thought the British PhDs were very good. I thought they were some of the best. And I think some of that has to do with their education system, the way they get weeded out as they go through school. So I always thought they were very good. I always thought the Germans were very good. I think the Americans have some stars. There's some very good American students, but a lot of American students are just so-so. I mean, they want to get in science, they do it, but they don't seem to have that passion, that drive, for whatever reason. Some of them are pretty good, but in general, I'd say a lot of the Europeans seem to have a little more, go get it, go do it kind of attitude, I would think. We have a lot of Chinese postdocs, and I think some of them do some really good work, but their problem's language. It's a problem. It really is, because they just can't write. They can't write, and it's hard to progress if you can't write. The ones that are stars, the ones that are exceptional, are able to write. It comes down to writing is the big skill. We have a lot of good Indian postdocs too. But again, I think language, again, is a problem. It comes down to writing. Is the lab really would love you to write, because if you can write, you can bring in money. And the other advantage of being an American postdoc is there's a whole lot of grants you can apply for in America because you're an American that nobody else can apply for. So they love, like I said, the American postdoc's the king, just because they're able to write different grants, they know the language, and it just works better in that respect.
More specifically, why I was asking is, in European PhD programs, they take only 3 years PhD program.
Okay. Well,
They still come up with a good publication at the end.
right. I think they're good though. I like all the ones I've ever worked with, I thought were very good. I don't know enough about the school to say, but all the European postdocs I've worked with are good, pretty much. You work with some bad ones too, but in general, they're pretty good. And like I said, Americans have stars, but in general, a lot of the Americans just, they just don't seem to have the drive as much, to some extent. The problem in America, there's a lot of other things that you can do. There's a lot of opportunities besides just science. And I think with computers getting bigger and bigger, a lot of Americans have steered towards computers. And business is big in America. So America in general, we like money a lot. A lot of people like money. And you can make a lot of money in business in America if you know what you're doing. So it's a draw where I think a lot of people that are very smart and would be good in science, just they never go there, because it's like, well, why would I put myself through 6 more years of school, a postdoc and a postdoc, when I could just get out of school, get a good business degree, find a good company, and make $100,000 a year? Why would I bother? So I think that's the thing you see. I'm not saying that works for everybody, but you do see a lot of, business people make some pretty good money with not that much extra education. So I think that's one of the things that keeps people out of science. And we also produce, like at my institution especially, our medical doctors are very good. It's a very good medical program also. So We have a lot of really good medical students too in America. It's very hard now to get into medical school in America. It's become very competitive, very very hard to get in. You've got to do the extra things you want to go to medical school in America. You've got to be a volunteer in a hospital. You've got to have done maybe some research. You've got to do things to set yourself apart. You just can't be smart. Because smart, there's a lot of people out there that are smart. It doesn't differentiate you anymore. You've got to put those extra things in. Okay, and like here, I think, like you said, you want to go to America, I mean, a good publication record out of here, of course, is going to help you for sure. You know, it comes down to, you know, people will look at what you do, without a doubt. So, you know, but a lot of it's individual, you know, the drive, the motivation, whatever. Like I know when Shrija was there, he worked constantly. He did. He worked a lot more than a lot of people. So, I mean, I think it paid off too. So, it comes down to that effort. I think it's really the bottom line. Propydium iodide is a good dye that tells you what about a cell? That's what? That's dead. Exactly. Okay. Okay, this is a two-part question. We'll do this as two parts. This will be two questions. Okay. To get an accurate measurement, you must do what to your microscopy system? You must calibrate. Exactly. Using what do you use to calibrate? It's like Jeopardy. You guys have Jeopardy here?
Yes.
Okay. But you've seen Jeopardy, like you have to hit the buzzer, and then you're allowed to answer the question? Well, you have to beat everybody. You have to answer the question. Okay, so let me ask you. I think you had your hand up. Micrometer, okay? Okay. To quantitate in modern biology, you need to use what? Bit depth. For it to be accepted for publication, you have to use what bit depth? What was it? 12. Okay. Everybody answers that one. Okay. Okay. The difference between the excitation peak and the emission peak of a fluorophore is called what? Well, you already got one. You already got one. You already got one. If you already got one, you got to keep your hand up.
Stoke Shift.
Okay. Stoke Shift. Okay. Okay. Okay, now this one's a little bit, you're going to answer, I don't know, we'll see what the answer is. I'll take, you know, we'll see. Okay. What is co-localization? Co-localization, what is it? Go ahead, give it a try. Co-localization is what? Who's got their hand up? Who's got their hand up? Did you have your hand up? No? It is, that's part of it, but more than one fluorescent dye, I don't know if I explained it correctly actually. That are where? Overlapping, right, they're in the same location, okay? So a part of that I guess I should explain, I usually use this example too. Like on a wide field microscope, if I said this is protein A, okay, and this is protein B, so right now you'd look and you'd say they're not co-localized, right? Because they're not in the same place. They're not co-local. They're not in the same location. So you'd say, okay. Now, in a wide field microscope, if I went like this, and now you looked from where you're sitting, what would you say? You'd say they're co-localized, right? But in reality, with the confocal, where you can look at it in 3D, you'd realize they're not. But in a wide field, you'd see it this way, and you'd say they are. But in a confocal, you'd realize they're not. Okay, so co-localization. To do a time-lapse experiment in multiple places on your sample, you need what type of equipment attached to your microscope? You answer. Wait, anybody? Anybody? You answer too. You answer too. Wait, anybody else? Anybody else? Yes. So if you answered, you gotta. Okay, now this goes back to yesterday, so we got to think backwards. We got to put on our thinking caps. What is everything? I don't even think we got that one. Everybody knows that one. I've said that how many times? Okay. Oh, okay. What are the three colors that make up a 24-bit color image? Red, green, blue. Okay. I got that one. I followed the rules. Okay. Okay, TIFFs are for blank, while JPEGs are for blank. What? TIFFs are for? Yes, and JPEGs are for? Exactly. Right. You guys pay good attention. I'll give you that. You definitely do. Okay, now this one's a little tricky. This could be the grand prize of the day. But you got to raise your hand. Okay? Because this one I mentioned, but I mentioned it sort of in passing. Plus you got to think. We talked about 3 different ways to use fluorescence in a microscope. What are those 3 ways?
Antibody dye,
That's one.
fluorescent microscopy,
Well, not fluorescent microscopy, but fluorescent.
dye,
Well, that's antibody, but fluorescent GFP. And then what's the other one? I think you said it through dye, right? Okay. You tell me. I don't know. Okay. So what are we doing next? T?
No, we can make it in 2 parts. One
Okay.
software.
So what's his name? Sham? He's here, right?
Yeah. he's-
Okay. Okay.
And
Okay. So we'll split into 2 groups.
Yeah.
So how do you want to split into 2 groups?
2 or 3 groups.
You tell me. What do you think? That's a pretty big room.
Yeah.
You think 2?
Yeah.
Okay. So you guys ever do the thing like we used to in school when I was around? You go like 1, 2, 1, 2, 1, 2, 1, 2 to break into groups? Okay. So let's start here. So you be 1. Two. Who else? Who else?